Hello and welcome to this session. I am Dr. Akshay Kumar, and in this session I'll be discussing with you useful mathematical functions and notations which we use in design and analysis of algorithms. In the previous session, we have discussed about the term complexity of algorithms. Now, in that, we defined or we used some summations, some term called expectations. So, we are going to discuss those terms in more details in this particular session so that you can utilize them whenever you need in the entire course of design and analysis of algorithm. Some of the terms which we will be discussing in this session are going to be summation and product, then function, logarithms, mathematical expectations, principle of mathematical induction. So these are the terms which we will be discussing in this session. Well, the very first thing which you should know is some of the sets which are declared. Okay, so the three sets which are most important and most used whenever you are dealing with, any of the subject related to design and analysis of algorithm, or most of other mathematical subjects are going to be, the three sets are the set of natural numbers, the set of integers, and set of real numbers. Well, the set of natural number is represented with the help of an n, right? And it represents the natural numbers, that is 1, 2, 3 till infinite, okay? Then comes the set of integers. Now, set of integers will contain negative integers as well as positive integers. All the values will be there. Then comes the set of real numbers, and in the set of real numbers you will get all sorts of real numbers, including fractional numbers, including square root of 2, that is irrational numbers, everything which comes under the set of rational numbers. So these three actually are represented as n for set of natural numbers, I for set of integers, and R for set of real numbers. Okay. Then comes a very important summations which we use. It is basically sum of sequences which we use. And if you remember, we last time in the last session we summed up 1 plus 2 plus 3 till n, right, which is summation of I equals to 1 till n for I is given as 1 plus 2 plus n, and it is n into n plus 1 by 2. The second is the sum of I square over I equals to 1 till n. Obviously, it is going to be represented as 1 square plus 2 square plus 3 square till n square. And the sum of this sequence turns out to be n into n plus 1 into 2n plus 1 divided by over some completely, this complete thing is divided by 6. Then the third term which we use is the sum of I cubes where I varies from 1 to n. Okay, so it is basically 1 cube plus 2 cube plus 3 cube till n cube, and it is represented as n square and n plus 1 whole square divided by 4. The third thing which we would like to discuss about the sequences is how do we represent products, right? So if there is a product of 1 into 2 into 3 into 4, basically up to n, it is represented as pi from I equals to 1 to n I. This is a very important terminology, or very important what we say representations which we use, which we put when we are doing the sum of sequences. Okay. The next important part is some useful functions, and the very first useful function is floor function. Now floor function, suppose given a real number x, the floor function is represented with the help of x, and there is in the bottom you can see there is a slight edge coming out, right, at both the sides, towards the inside of it. So this is called the floor function. Now what does it do? It maps each real number x to greatest of all integers less than or equals to x. Now this looks very complex, so look into the example. So suppose I am looking for floor of 3.5, it is going to be 3. I am looking for floor of 3.8, still it is going to be 3. I am looking for a floor of minus 3.4. Now when it comes to minus 3.4, the greatest of integers less than or equals to x is going to be minus 4, not minus 3 in this particular case, because minus 3 is higher than minus 3.4. So you are looking for less than or equals to the greatest of all integers which are less than or equal to, and that is going to be minus 4. So you need to be careful when you are dealing with the negative numbers. Otherwise, it is very simple that you truncate the decimal part and you get the floor value. As far as ceiling function is concerned, the ceiling function is represented as what you can see, it's just like almost a bracket, but the bottom part is missing, right? So you just see the notation. It maps each real number x to the least of all integers greater than or equals to x. That means the ceiling, okay, the ceiling of 3.5 have to be 4. The ceiling of minus 2.4 has to be minus 2. Okay. And a very important thing over here is going to be, please understand, x minus 1 is less than floor of x, which is less than equals to x, which is less than equals to ceiling of x, and this all ceiling of x is less than x plus 1. For example, if we take a number x as 3.5 and another number x equals to 5. So first let's do it for 3.5. Okay, so what is x minus 1? It is 2.5, right? So 2.5 is less than its floor, which is 3.5's floor is 3, which is less than the number 3.5. The ceiling of this number is 4, so 4 is greater than equals to 3.5, it is greater than 3.5, and x plus 1 is going to be 4.5, which is greater than definitely 4. Now has it been just 5, then 5 is definitely greater than x minus 1, which is 4. Now 5 happens to be the floor also, right? So 5 is equals to 5, okay? And the ceiling of this value 5 is going to be 5 only, right? Which is less than 6. So this is a very important example which basically will make you understand what this particular thing means. The next term which we need to discuss is called the logarithm. Logarithms are widely used in the analysis of algorithms. The properties of logarithms can be derived from the properties of exponent basically. So if you know exponent, the logarithm is just the opposite, or not opposite, but then just very similar to it, because it is drawn from the exponent. So if we want to define logarithm, take the case if b to the power x is a, then if we take log of a with the base b, so b for which we are finding the exponent value, right, earlier. So log of a with the base b, okay, it is going to be the value x. Note one particular thing, b has to be greater than 1 and x is positive in all these cases, right? So b, in any case, if we say b to the power x, b is the base of that particular representation or exponent. Okay, and a is the value. So now it is slightly reversed, that you are taking log of a with the base b, all right, and it is equals to x. And once again, the value b is always greater than 1 and x is positive. So log has several properties. And one property which we have proved here, and others we have shown, but you can see other properties also, like if we are taking log of b and c together, okay, and having the base a, then it is same as it is equals to taking the log of b with the base a plus log of c with the base a. Now, just to prove that, if we take log of a bc equals z, let's assume that, and log of b with the base a. So base is a, so I'm not going to say what base we are referring to. So log bc equals to z, log of b equals to x, and log of c equals to y, and everywhere the base is a. Then since base is a, so if we convert it into the exponent, it means a to the power z becomes bc. So a to the power z equals bc, a to the power x equals b, and a to the power y equals to c, right? And if I say this particular thing, okay, now b is basically a to the power x, c is a to the power y, so we replace in a to the power z equals to bc the value of b and c. So what we get? A to the power z equals to a to the power x multiplied by a to the power y, and as we know the rule of exponents, we simply need to add the exponents in this particular case if the base is same and we are multiplying them. That means a to the power z equals to a to the power x plus y, which implies the value of z equals to x plus y. Now what was z? Z was log bc. What is x? Log b, and y log c, log a, and hence you have proven the basic corollary that log bc with the base a equals to log b plus log c, both having base a. All right. Similarly, there are many more properties of algorithms, that if you are taking log of b to the power n, okay, on base a, then it is equals to the n, which is the power, it comes out. So it is n times of log b with base a. And you can change the base also as far as log is concerned. For example, if you are taking log of p with the base a and you want to change it to log to base b, then it can be log p with the base b. However, you need to divide it with log a with the base b. Okay. Similarly, there are few more properties which you can see in the slide, and you can refer to those properties if you want to prove certain basic theorems about logarithm, or you want to use logarithm to design a particular complexity of a particular algorithm. Now, another function which is quite popular and used in fact, analysis of algorithms, and in fact in designing of algorithms, is mod function. Well, mod function returns the remainder after a number called dividend is divided by another number called divisor. So if n is a positive integer and b is any integer, then b mod n, okay, b mod n equals to r, where r is between 0, r is greater than 0, but r has to be less than n, because that is what the divisor is, and okay, and b is going to be defined as k, which is going to be your value or which comes out after division, k into n plus r. Okay. There are several examples given over here, right. So, suppose b is 42 and n is 11, then b mod n is 42 mod 11, okay, is going to be 9, okay, as 42 can be represented as k happens to be 3 in this particular case, 11 3s are 33. So, the remainder is 9. So, that is how the mod function works. So, you divide basically, and quotient is basically is not shown in this particular case. Okay. So, quotient is actually 3 and you actually show the remainder. Okay. And had it been the value of b, if it is minus 42 and n is still 11, in that particular case, what you are going to do? You are going to divide the dividend or the quotient is going to be minus 4, okay, because minus 44 is less than minus 42. So, that is how you need to be very conscious of the fact that whenever you are dividing negative numbers, okay, you need to make sure that you do the correct mod or correct value comes out over here. Okay. So, this mod function you can use in many situations. Okay. For simple algorithms also, mod functions can be utilized for checking if there is a particular number is completely divisible by, let us say, 2 or not. Okay. Then comes the mathematical expectation. This particular mathematical expectation we used when we were defining the average case complexity. Well, mathematical expectation is used while computing the average case analysis of algorithms. Example is, for example, this example is distribution of marks of student who completed MCA in 2024 is given in the attached table. If a student is picked up randomly from the set of students under consideration, what is the percentage of marks expected of such a student? So, the marks distribution is given, okay, where range of marks in percentage is defined and the number of students or the percentage of students who scored in that range. So, 0 to 20% of marks were obtained by 8% students, 20 to 40% marks were obtained by 20% students, 40 to 60% marks were obtained by 57% students, 60 to 80% marks were obtained by 9% student, and 80 to 100 marks were obtained by 6% students, right. Now, our objective, okay, so these values looks fine, but the question is, let's scan the table and what you expect, okay, suppose you pick up just one student. So, we intuitively will expect the student to score around 40 to 60% of marks, right, because more than half of the students have scored marks in that category, okay. So, that is what is the main essence of finding the mathematical expectations. So, that is intuition, but how do we mathematically compute mathematical expectation? So, for a given set S of items, each item is associated with the values say V1 to V2 till up to Vn. Let the probability of occurrence of an item with value Vi be Pi, then if an item is picked up at random, then its expected value is given by EV, which represents expected value of V, equals sum from 1 to n Pi Vi, which means it is equals to P1 into V1 plus P2 into V2 plus P3 into V3 up to Pn into Vn. So, that is the way we compute the mathematical expectation, and it is very important to compute mathematical expectation in several cases where you are just trying to find a probable value in a particular situation. Let's take an example once again, the example of the percentage marks which we were discussing, right? So obviously the marks range as was given. So since we have to, what was the formula? Formula is P1 into V1 plus P2 into V2 and so on and so forth. Now what is the value when it is 0 to 20%? The range is 0 to 20, right? So what is going to be our class mark which we represent? The class mark in this particular is going to be the mid value, which is 10, right? So 10, and what is the probability? Because 8% we are referring to, so between 0 to 20 we have 8%, right? So it is 8 by 100. So probability of occurrence is 8 by 100. So it is 10 into 8 by 100. And the class mark in case of 20 to 40 is 30, right? Mid value. It is 30 into 20 into, because 20 is the number of students, percentage of students who have obtained the marks between 20% to 40%. So 30 into 20 by 100 plus 50, likewise it is the mid value 50, then 70 and 90, and multiplied by related the percentage or the probability, which happens to be 57 by 100, 9 by 100 and 6 by 100 respectively. And the average, or when you sum that up, okay, when you compute the final value, what you will get is 47, right? So it basically is referring to 47 marks, right? So this 47 marks basically represents the value between 40 to 60, right? And that is where the 57% student scored the value. And the average for this particular or expected value of percentage of marks turns out to be 47% marks for a student. Okay, so this was the concept which we had discussed about the expectation. Now let us discuss a very important concept and principle which we use in computer science most often for proving a particular situation. Okay, one definitely is contradiction, but principle of induction is most used, one of the most used way of proving certain mathematical fact. Well, mathematical induction is a method of writing a mathematical proof generally to establish that a given statement is true for all natural numbers. So that is what is the basic purpose. Okay. So basically we are trying to prove it for n, or the set of natural numbers technically. However, you can do it for other situations also. This particular method of principle of induction consists of three major steps. Okay. The first step is called induction base. Now in this stage, what we do, we verify or establish the correctness of initial value, and this is called the base case. Okay. So basically what does we do in this particular situation? It is the proof that statement is true for n equals to 1 or some other starting value. Sometimes it can be 0, sometimes it can be 2, whatever may be the case. Okay. So the first case is basically the induction base. The second step is then induction hypothesis. Now, induction hypothesis is an assumption which we state that the given statement is true for any value of n, where n happens to be anything greater than equals to 1. Okay. So we assume, we state this particular value to be true for any n value, and then we perform the induction step. Now in this induction step, in this stage we make a proof that if the statement is true for n, it must be true for n plus 1. So, we prove it correct for n plus 1. So, let us take a very simple example of the series or the sum of the sequence, right. So, let us prove using induction that the sum of first n positive numbers is n into n plus 1 whole thing divided by 2, that is 1 plus 2 plus 3 and so on till n equals n into n plus 1, and this is divided by 2. So, what is going to be the base step? Let us show that the given equation is true for n equals to 1. So, when we take n equals to 1, only one term is there and the value of that one term is 1. And what is going to be value of n into n plus 1 by 2? Since n is 1, so n is going to become 1 into 1 plus 1, which is 2 by 2, which is basically 1. So, hence the first condition, that is the terminal condition, is true. Now, let us do the induction hypothesis, and we assume that the given statement is true for n, a value n. And induction step is, now we need to prove that the statement would be true for n plus 1. So, the statement basically goes like this. So, it is 1 plus 2 plus 3 plus and so on till n, that was already there, and we add n plus 1th term, which is n plus 1 into it, and the sum of n terms was n into n plus 1 by 2, right. So, it is equals to n into n plus 1 by 2 plus n plus 1, which we have added, right. So, that is how it should be, it can be proven. Okay. So, the right hand side you see, then we say we take 2 common, and what we get, n into n plus 1 by 2 plus 2 times n plus 1. Okay. And when we take n plus 1 as common, we get n plus 2 in the bracket divided by 2, and this can be represented as n plus 1 in parenthesis, and in once again n plus 1 plus 1 in another parenthesis divided by 2. This is what represents sum of n plus 1 terms as far as the mathematical equation goes. Okay. So, what you have proven is that this particular that is the summation up to 1 plus 2 plus 3 plus n equals to n plus 1 by 2 is proved, because we assumed it for n and we proved it for n plus 1. Okay. So, this is proved, hence proved by induction that this is a correct sum. So, this is the way you can utilize induction in these kinds of situation. So, let us now try to summarize that what we have tried to do in this particular session. So, in this session we have discussed about some of the basic mathematical function and notations that are used in design and analysis of algorithms. In this session we have discussed about the floor function, the ceiling function, the summation, okay, the summation and the products which we use, okay, of sequences. Then we have defined the term mathematical expectation, which is one of the very important thing which you are going to, or very important concept which you are going to utilize during while finding about the things, or finding about the complexities of many situations. And we try to prove principle of induction to prove the sum of sequence 1 till n as n into n plus 1 by 2. Now, you can do it for, or you can try it out for n square, sum of n square, okay, that is summation of I square, which we had defined. You can try it for summation of I cube. Okay. So, like that, now you can try the induction on various situations. Now, with this we end this particular session. Thanks for being with us.